In this lecture, we're going to talk about two very important problems in computer science, searching and sorting for things. And they're actually quite related. If you look at the photo here of the library shelf, right, if you had to search for something in a library shelf, you could probably do it pretty quick, but only if somebody had sorted the books beforehand. So if they were in like alphabetical order, or they were in the Dewey Decimal System or something like that. If they were just a random, if all these books on the shelves were just, randomly strewn about, you'd have to spend quite a long time trying to find a book. And we'll look at different ways you can search and sort in computer science, and sort of what the implications are about how you do it. So the first way you might think of doing a search, okay, so I'm going to look at search first, and then we'll look at sorting. The simplest way you might imagine doing it, say you're looking for some key value, and you're looking for, oops, sorry, I forgot I can't click there. You're looking for this key here, all right, and you're looking for it in a string, an array of strings. Simplest thing you could do is just loop through all the index positions of that array and see if you found it. That's what the compare to key does. It just goes from I equals 0 all the way up to the length of the array and looks for it, and when it finds it, it returns it. If it doesn't find it, it returns -1. It's a simple algorithm. It's easy to see it's correct, and it's easy to code up. Here's a potential application for a search. Imagine you're doing, you're checking whether some email address is in a whitelist, so it's an email address that's allowed to come in. It's not from a spam address or something like that. We could read in a list of, we have a very large list called a white file that has all the good email addresses, and then we're going to get from standard input a list of email addresses, and we're going to find out which of these, sorry, here are the ones we want to check, and here's the white list, and when it goes through here, it's only going to output things that weren't in it. So these are, I guess, potentially evil or spam kind of addresses. Okay, so it goes through everything in the standard input file and checks and sees if it's in the whitelist or not. All right. Here's another application of that. You can imagine you're a credit card company and you're doing 10,000 transactions a second, and you're looking through 10 million card numbers to see is this card number one of the valid ones that's in your customer records. You could do this with sequential search. You could have a big 10 million size array, and then just go from index position 0 and go all the way up to 10 million looking for it. What kind of computer do you think you would need to achieve this, though, to support that rate? So you're doing, you're looking through 10 million things 10,000 times a second. Well, turns out you better have a supercomputer, or a Google server farm, which is, essentially a supercomputer. Supercomputers these days tend to be giant farms of servers, but that's what it would take for this credit card company to do this with that many account numbers and that many transactions per second. All right, so we need a better way, and the better way, and the way you look for those books in the library shelf, is to look through something that's already sorted. And if it's already sorted, it really makes it a lot easier to find what you're looking for. We'll see. It's actually more expensive to do the sorting, but once it's sorted, okay, if you've got an array that's all sorted, you don't have to look through the whole thing, right? Just like you don't have to look through all the names in a phone book. You start in the middle and then see if you have to go in the first half or the second half, and then if you decide, oh, I got to go to the first half, then do you go to the first quarter or the second quarter? You just keep bisecting things, looking for your target value. All right, and binary search works exactly like that. We've got a sorted array, say all words in alphabetical order. We're going to have some low value, which is the lowest index we're currently considering, and then some high value, and then we're going to have a midpoint. And initially we're going to set the low to be the very first element in the array, and the high to be, high is one more than that, so high minus 1 is the last valid index in the array. Then we look at middle, and what we're going to do is we're going to see, well, whatever we're looking for. Say we're looking for, I don't know what we're looking for in this example, query or something like that. We're looking for the word query. We're going to first see what is at our midpoint position, and is it what we're looking for. And if it is, well then hooray, we can return the index and we found it. Otherwise, we need to decide, should we search in this top half, or should we search in this bottom half? And which one we search in really depends. Since this is sorted, we can just compare and say, well, I'm looking for query, and query comes after M in the alphabet, so if it's gonna be anywhere, it's gonna be in the second half, and we bisected our search. This is exactly the same thing you do when you look up a name in a phone book. Here's the Java implementation for this. It's got basically, we've got this public method. This is one you call. I really actually should change this, make this a private helper, but never mind. The user calls this search public method with the key and an array of strings, and what it does is it calls this recursive helper method, and this recursive helper method repeatedly plays that game. At first, this is kind of a failure condition, so if your high is ever less than or equal to your low, then you know you haven't successfully found it. Okay. The midpoint, well, how do you compute the midpoint? Well, you take the difference between the high and the low, divide it by 2, and then add it to the low. So that takes that range and gets you right in the middle index position of that range. We then compare. Okay, we compare whatever's at that midpoint with our target. All right, and compare to will return a positive number, -1 or 0. So it returns 0 if you found it. So this is this final case where we actually return it. But if it's greater than, okay, we know that the midpoint was after what we're looking for, so therefore we should look in the lower half of the array, versus if it's less than that, then we need to look in the upper half. So this is the thing that bisects, and then we go from low to mid. So this will actually look from index position low to mid -1, whereas this one will look from index position mid +1 up to high -1. Okay, so you see we've just eliminated that midpoint because we've already compared it, so it can't be that one. All right, simple, right? It's simple, but it's also easy to get wrong, as this quote talks about. I mean, there's a lot of little problems you can, little bugs you can insert into this binary search algorithm, and so if you're going to use binary search, you could use, there are already implementations in the Java library for doing that, yeah, just be careful if you're implementing it yourself. How much better is binary search than linear search? Okay, if you have an array of size n, every time you compare, all right, at first you don't know where it is, it's somewhere in that n. But after you do one compare, you know it's in now an array of size n over 2. All right, it's in one half or the other. All right, you've cut your search space in half, and you continue to cut it in half every time you do a comparison. All right, how many times could you divide a number by 2 until you reach 1? Well, if you remember your math, that's actually log base 2 of n. Okay, and what's really good about log base 2 of n is even if this number is really big, like 1024, it divides and reaches 1 in a very short number of steps, right? You divide it once, twice, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times, 9 times, and 10 times. All right, 2 to the 10 is 1024. Okay, and you very rapidly, even for a billion, log base 2 of a billion is a small number. Okay, we really like things that are log n. Alright, so here's the same problem again. You're the credit card company and you're trying to look for those customer numbers in your 10 million numbers, and you're doing 10,000 transactions a second. What kind of computer do you need now? With binary search, all we've done is change from that one algorithm that was maybe 3 lines of code, right, to this algorithm, which is what, 6, maybe 7 lines of code. All right, slightly more complicated, a little hard, a little harder to do. But what can we run on now? Well, you can run on anything from your cell phone on up. Okay, your cell phone's powerful enough to do this. That's how good log n is versus a linear search, right? A linear search is always going to have to go through all, on average n over 2 of them, right? Or if it's in there. If it's not in there, it's going to have to go all over all n of them, all right? Okay, so that's searching. I'll show you. I've got a little demo. Let me pull up my Eclipse. Here is the linear search, all right? And then I've put in the binary search. I just named it so there's not a collision, okay? Binary search, and I made this little private helper method. All right, this is the same whitelist problem. We're going to read in a file. That's what this in class does. Okay, reads in the file, reads in all the lines in the file, reads in all the data in the file, and then splits it into words. Okay, then it's going to read in, while there's stuff on standard input, it's going to check and see if that word's in the whitelist, and if it's not, it's going to print it out. So that is, it's going to print anything that isn't in the whitelist. To do this, what I've got set up here is I have a dictionary file. Okay, all right, there are 330,000 words in this dictionary. Okay, and here's the beginning of it, and it is sorted. Okay, you get all kinds of words in there. Okay, aberraticulations. Oh boy, aberraticulations. Okay, I shouldn't even tried to say that. Okay, so what are we going to compare it against? What other file did I put in here? Okay, I've got the text of Moby Dick. This is just going to look for essentially misspellings, or actually I'm not actually getting rid of punctuation or anything, so it's going to find all those too. But for sake of an example, we'll run that. We'll send in that dictionary file, and then we'll go through Moby Dick. Okay, and it starts printing stuff out, so it seems to be working. Okay, we don't want to wait forever just to watch it scroll, so we'll do this. Okay, boy, seems like it's taking a little while, doesn't it? Okay, remember, I'm using the search method here, and this search method is doing the linear search. So every word it encounters in Moby Dick, it's going through those 330,000 words looking for it. Okay, and sometimes it finds it and sometimes it doesn't, and when it doesn't, it has to go through all 330,000 words. All right, I'm not even going to wait for this. How many lines did we get? We got about 1,000 words. Okay, let's go and change that. We'll change it to binary search. All right. Now we'll run the same thing. Okay, and it's done. Okay, how many lines were in the output? Close to 59,000. All right, we were not even a a little over a 60th of the way there. Okay, that's the difference between log n and n. Massive difference. How did I sort that dictionary file though? Okay, maybe those words were all mixed up when I started. Sorting is another fundamental problem in computer science, and the game is to arrange n items in ascending order or descending order, if you like. Okay, and this occurs everywhere in computer science and in all kinds of different scientific problems. You just can't do any. It's a building block for a lot of algorithms. Here's a simple way of doing a sort. It's called insertion sort, and it's kind of a brute force thing, just like linear search is a brute force way to search for something. And the way it works is it moves left to right through the array. Okay, this is actually a view, part of the way through exchanging elements. And what it does is it finds the next one it's working on, so it's going to work on the word the, and what it's going to do is just exchange elements until the gets in the correct position. So it's going to say, well, the and you are out of order, so I'm going to swap them. Okay, was and the are out of order, so I'm going to swap them, and then his and the, they're in the correct order, so then I can stop. Okay, that was handling putting this word at index position 6 into the correct spot. Okay, and then once that's done, it would go and do the word but. That's the basic story, and here's a diagram showing it doing it from the beginning. Okay, the first row is all those words not sorted. It's going to start at this had and say, well, is had in the correct order with was? No, I'm going to swap them. Okay, now we're done with that. Now let's deal with him. Well, is him in the right order? No, I need to swap it with was. All right, and is is it him still in the right order? Yeah, it's okay. All right, comes here and does and gets swapped, okay, and then swapped again, and gets swapped all the way to the front. All right, and then U doesn't have to get swapped because it's after W in the alphabet and so on. And you can see each of these blue ones is inserting this new guy. Okay, we're going left to right through this, and we keep inserting this new guy into its proper spot by just playing this game of exchanging. Pretty simple. Here's the Java code that implements it. We've got our outer loop going from I1 up to the length of the array, and then we've got the J that's going backwards and doing the compares and then doing the exchange. This little static helper just does that exchange of the two strings. Okay, so it has a little temporary variable, stores something off, and then does the swap. Pretty simple. Okay. How long does it take? Well, it depends actually. Okay, and this might be a bit surprising. It depends on what you started with. It can take, a long time. So n squared, as we learned in our performance analysis, is not so good sometimes. For large n, it's going to take a very long time. If these things are in descending order, okay, that's kind of the worst case, where we have to swap all the way through. Okay, every time we get to that new guy, we've got to swap him all the way back to the front. Okay, versus on average we'd only have to do that about half as often. Okay, halfway through. And in the best case, well, somebody just handed us an array that's already sorted, in which case every time we look at the new guy, we just say, oh, well, we don't need to do any swapping. Okay, and that's the best case, would be order n. All right, but remember, this means somebody's asked you to sort something that's perfectly sorted. All right, and okay, that should be pretty cheap, right? You've got no work to do. And here's the graph showing the the order n performance, and here are the two that are n squared, and they have the same kind of curve. They're just off a little bit due to the constant factor. And remember, this is a log plot here. Yeah, and here's just a diagram showing that worst case behavior. Okay, when this thing is completely out of order, all right, we've sorted all these, but now we have to do D. Well, D has to swap with J, and then it has to swap with I, and then with H, and then G, and then F, and then E, and then D is in order. Hooray! Then C. Well, C has to swap with J, and then with I, and all the way back. Okay, and you can add that up and calculate that's n squared over 2 compares. On the average, it's not going to be so bad. You're only going to have to go half the way, and so that's how you get the n squared over 4. Credit card company wants to use binary search for looking for this card number. Problem is, they need to sort the data. If they use insertion sort, what kind of computer are they going to need? Well, okay, you probably guessed it. You need the supercomputer or the Google server farm to pull this off. All right, sorting 10 million things with an n squared algorithm is going to take a long time. The lesson here is, don't think you can just buy your way out with a faster computer. Okay, computers are only so fast, and even if you had that supercomputer and say you could do 10 to the 12 comparisons a second, many orders of magnitude more than my laptop, all right, you're still you kind of did all right here. Like if you had 1 million, okay, your laptop takes a day, but the supercomputer is so super fast it only takes a second. Okay, but if you go to 1 billion, all right, 3 centuries or 2 weeks. And 2 weeks is still a long time. Okay, a bad algorithm is a bad algorithm, and you can't get yourself out of it just by buying a faster computer. Moore's law is a sort of a famous rule about how fast things get, how fast computers get faster, I guess. And it's related to transistor density, so it's doubling every 2 years. And people have all kinds of variants of this law. Things like memory and disk space and bandwidth and computing power per dollar all tend to double on some kind of time span like this. Okay, and this is showing calculations per second for $1,000. All right. And you might think, well, Moore's law will bail us out. We don't need good algorithms, but things are just not, I mean, you may get a computer that's 10 times as fast, okay, but you know, often in step with that, people are trying to solve bigger and bigger problems, okay, and it's you know, inefficient algorithms can easily outpace what Moore's law is able to provide in improvements in computer hardware, okay. To really attack a lot of problems, you need linear or linear arithmetic and log n algorithms to keep pace with that, you know, with Moore's law. Right? You just can't get away with using an n squared algorithm. How do you sort efficiently then? Okay, n squared is too slow, and we've seen this, I think, we've seen this before, the merge sort. So let me explain merge sort again. What you do is you divide your array. It's a divide and conquer algorithm. You're going to divide your array into two pieces. All right, you're going to hand the two pieces off, and somebody's going to recursively sort those. Okay, and once they hand them back, they'll be insorted. So you have two halves; they'll both be sorted, and then you just do the merge operation. And it's actually, you know, that's a lot easier once somebody has given you two piles of, you know, if somebody gives you two piles of cards that are already sorted, it's easy to merge those a lot easier than if you had to sort two random unsorted piles of card. How do you merge efficiently? Well, the easiest way to do it is to have an auxiliary array, and this is this column here, auxiliary. All right, we've got two arrays. Say somebody hands us this half, and they're both sorted, okay? And our goal is to create one array that's completely sorted. And it's pretty simple, right? We just start with sort of a pointer to this first guy and a pointer to this first guy in this half, and then we just see, well, is it and or but? Well, it's and. Okay, so that gets to be the first guy. All right, and so now is, you know, what's the next guy? Well, but versus, you know, had. Well, but it comes before that. Okay, had versus his, that's had. Okay, you just take one or the other, leave one guy alone, and then advance the other guy, and eventually you move all the way through both of them. And when you're done, this auxiliary array will have the merged sorted list of things. And here's some code that does that merge. You see, we set up our auxiliary array at the top, and then we just make our way through, okay, comparing those things, and then adding the one that's you know, adding the one that's the lowest in there, and then carrying on, and then just being careful to, you know, always add them all, okay. You know, so if you run off the end of one of them, then we just keep adding from the other one. Okay, so once one of these guys is completely exhausted, then you have no choice but just take it from the other side, right? And then once you get it in your auxiliary array, you just copy it. You can copy it back to where you got it from if you want. And so with that merge, okay, the merge is really the hard part. The rest of it is divide and conquer. So if somebody asks you to sort something, okay, you just call, you know, and again, maybe I should have made this a private helper, but you just call this guy, and this guy splits it in half. Okay, calls himself, you know, calls itself recursively, sorts each of those, and then does the merge here. So that's that merge algorithm I showed you on the previous slide. Simple as that. Okay. You know, I think this is actually simpler to understand than, you know, if you understand recursion well, it's actually simpler, this algorithm, than say insertion sort, maybe. The analysis of merge sort, how long does it take? Well, think about what's happening. At every stage, we're splitting into two. Okay, so we start with n things, and we have n over 2, and then we have n over 4, and so on. How many levels are in this tree? Well, just like binary search, you keep dividing by 2, so you can't do that very, you know, many times until you get down to 1, or in this case, you know, we'll call maybe 2 is the, you know, base case or whatever. You only have log base 2 of n of these levels. All right, and that's how many levels and how many things you need to do in each of these. Well, each of these are going to involve doing that merge, and the merge is going to need to do as many compares as there are things you're trying to merge, right? So there's n over 2 here, and you're merging with n over 2 here, so it's going to take 2 times n over 2 to merge. Well, that's just n. and there's 4 of these guys, but they're n over 4. Well, that's just n. So each of these guys is really n compares. So we have log base 2 n levels, and we have n compares at each level. So that's what gives us an n log n performance of merge sort. And it turns out it can't do any worse than that. No matter what you get, even if you give it sorted data or unsorted data or random data or any data you choose, it just does what it does, and it takes n log n time. Okay, and this is nice. There's a constant factor difference here, but no matter what, best case, worst case, average case, it always performs about the same. All right, and you can validate that running some experiments on different size n. Here are the actual some actual times or something, and then the actual predictions. So the actual theory from the mathematical analysis agrees with what you see when you actually do empirical performance analysis on it. All right, so same problem again, sorting things. So with merge sort, well, what can you do it? Well, again, you can do it all the way down to your cell phone. Okay, and maybe even your toaster, if your toaster was sufficiently advanced, maybe has a little touch screen and a microcontroller in it or something. It could probably do it too. All right, and here's a little video you can. I won't show you this in the video, but if you want, you can check out this YouTube link here and see President Obama answering a question about sorting a million integers. And so you can look up. He's talking about bubble sort, which is a similar simple algorithm, kind of like insertion sort. Take-home message for this lecture really is that a good algorithm is way better than a fast computer. Okay, clever algorithms trump supercomputers every single time. Okay, and you can see it here, like doing sorting on a billion things. If you have insertion sort, okay, it could take weeks, but only takes 3 hours on a laptop or instantaneously if you've got a Google server farm. To summarize, we looked at 2 very important building blocks for many problems in computer science and other engineering disciplines. How to search for things efficiently, and we do that usually using binary search. And binary search requires that what we're searching be sorted, and so we need efficient ways to sort. And one way to do an efficient sort is merge sort. And all these fancy applications you use every day out on the web, well, they're really enabled. The only reason Google or a lot of these other companies can do their job is because they're based on algorithms that scale to large amounts of data, and those algorithms are things like binary search and merge sort.